Hello, everyone. It's nice to be here, even though here is not the same for you and for me, but okay, we can still discuss. Let me also thank the organizers for insisting and putting together this nice conference. So today I want to tell you about quantum non-locality in networks, which is an area that has started interesting people about 10 years ago or so. And so I hope I can convince you today that there is some interesting physics there, and in fact, many opportunities for open questions and finding interesting results. So here is a list of the people that have been involved in some of the works I will present today. And of course, I will also refer to works of other groups that have been thinking about these interesting questions. So what do we want to do? Well, we are interested in Bell non-locality. So here you have a picture of John Bell with his famous Bell scenario, as we call it today. So as a reference, I often call this the standard Bell scenario, right? So this means that you have something like this. You have one source producing some quantum state, possibly entangled, that is distributed to two distant observers, Alice and Bob, who make some measurements on these systems, right? So as you know, when you use quantum systems, you can get correlations there that defy your intuition and that cannot be explained by in classical physics, right? So that's the effect of non-locality. And so now here we're interested to do to investigate this phenomenon in the case of networks. So this means I will now consider a case where I have not only two observers, but many, right? So one idea would be to do something like this. So one network with a central source distributing a big entangled state to many different parties. So this is in fact something that has been known since a long time. This is multipartite non-locality, where people like Mermin and GHZ, Svetlichny did many interesting things already a long time ago. But here we want to go in another direction, namely go to networks that look like this, right? So you see the difference is that instead of having all the parties connected by single source, right, we have several sources now in the network, and each source connects only subset of parties, right? So this is what we are interested in here. So the main difference is this: how the sources distribute the resources, right? In standard non-locality, we have one source, and here we will have many different sources which are independent from each other. And so this may seem like a small extension, but in fact, it changes everything. And so what I mean by that is that in the standard multipartite non-locality case, we have, I would say, good understanding of what's going on. I'm not saying we know everything, but okay, we have a general understanding of the problem. And this is mainly due to the fact that the problem is convex. So it's linear, and there we have very efficient methods. Now, when we turn to networks, because of the independence of the sources, the problem becomes non-linear. Sets of interest are non-convex, and it's extremely difficult. So yet we know a few things that highlight to the fact, I think, that there is really interesting new physics here, and this is essentially what this talk today is about, to give you an introduction and a flavor of this new research area. So what I want to do is, start with the beginning. So how do we define locality? So how do we define classical correlations in a network? And then go to quantum non-locality. And in particular, I'll spend quite some time today to try to convince you that there are really new forms of non-locality that can be present in a network. And this is an effect we refer to as genuine network non-locality. And so in the end, if there is time, I will also tell you about no signaling. So how the no signaling principle emerges in the context of networks. Okay, so let's start with a very quick recap on Bell non-locality, just to let you see my style, my notations. In Bell, we are first interested in local correlations, right? So if we again view such an experiment with a source producing a classical variable denoted lambda, right? The locality condition of Bell is the following. So it says that the observed input-output distribution should admit a decomposition of this form, right? And so we can think of these local correlations geometrically. They take a very nice and simple shape, which is a convex polytope for the experts here. And essentially, well, the point you see is that this is a shape that is convex and that can be characterized pretty efficiently. Then we go to the quantum case, right? So the source is now promoted to be a quantum state, possibly entangled. And the measurements of Alice and Bob can now be non-commuting or incompatible measurements in general. And this leads to quantum non-locality, right? Quantum correlations can be stronger than classical ones. Well, they take generally this form here from the Born rule, and usually we represent them like this, right? So it's again a convex set, maybe not a polytope, but it's a superset of the local polytope. And so finally, we have no signaling correlations. So correlations that simply satisfy the fact that they do not allow instantaneous transmission of information. And again, this forms another polytope bigger than all the others. Okay, so this is the usual picture we have in standard non-locality. We like to draw these little things here. And somehow now for the networks, we would like to have a sort of similar understanding, right? What is the situation? But as I said, because of the non-convexity, this becomes much more challenging. All right, so let's move to networks, and let's start with a simple situation. So I will only consider networks here with 3 observers, right? That's already complicated enough, as you will see. So if I have 3 observers, there are not so many different possibilities to connect them via network. So here is the easiest one if I have one common source, but this is what we've seen already, right? So this is the standard non-locality à la Bell. This is the locality condition. And okay, here we know everything. So one point you should note here, though, is the following. So if you see in this Bell experiment here, where I have each party receives an input and gives an output, if I were to remove the inputs, right? So that means every party performs a fixed measurement, then things become trivial, right? Why? Because any probability distribution for the outputs A, B, C, I can just obtain classically by sampling here in the source from that distribution, right? Now let me move to a more interesting network, which is the following. So it's, as you can see, it's inspired from entanglement swapping, right? So I have A and B connected by some source and B and C as well. And so if these sources were to produce entangled state and Bob would make here a Bell state measurement, this would be entanglement swapping, right? So now in this network, I can also think about how I would describe local correlations. And so the main idea that we want to use here is the fact that these 2 sources are independent, right? So we want to enforce the independence condition of these sources. And of course, this has important consequences on the distribution, because if I would trace out Bob here, of course, Alice and Charlie should then be independent, right? Because Alice and Charlie are only connected through Bob. So how does one go and describe local correlations in such a network? Well, that is the idea that came out as bilocality, proposed more than 10 years ago by Brancière, Gisin, and Pironio in this nice PRL paper here. And so you see the difference now is that we have these 2 hidden variables, these 2 local variables, lambda and mu, and you see their distribution here factorizes, right? So we assume that they're independent, and obviously now you see that correlations that admit this form, well, they are not convex in general, right? Because of the nonlinearity here. So characterizing these sets is pretty complicated. There exist now certain methods, but they are, not that efficient in general, I would say. Yet, so what Brancière and colleagues could show in their first paper is that there exist quantum correlations that are non-bilocal. So as such, this is maybe a sort of rather trivial statement, because bilocal correlations are a subset of standard local correlations, right? That have, sorry, let me go back, that admit this decomposition here. So you see any example of multipartite non-locality is already an instance of non-bilocality, right? So that is a bit trivial. However, what is much more interesting is that they showed that there exist quantum correlations that are non-bilocal, but yet they would be local in the usual Bell sense, right? So these are correlations you could explain via one common source distributing classical variables, but that you cannot explain classically when your classical variables must be distributed by these two independent sources, right? So this is the first and nice observation, that enforcing the topology of the network changes your statement about the nature of correlations. So now let's move to a third network, which is arguably the most fascinating one, so much more challenging. So this is the so-called triangle network, where you see we somehow started from bilocality, but we added this extra source here, now connecting also Alice and Charlie. Okay, so we get a triangle. And now you see I immediately started the discussion here by having a triangle network where parties take no inputs, right? They only provide outputs. So you see, before we argued that forgetting about inputs makes the problem trivial and non-interesting, but here it's not so. So here we can look at correlations without inputs, with fixed measurements, and we can conclude about quantum non-locality, for instance, which is a very interesting phenomenon, I think. So let's first define what are local correlations or classical correlations here. Well, if you understood the previous case, you directly understand this one. It's the same idea. We have three sources and we assume they are independent, and therefore the distribution of these local variables must factorize. Okay. All right. So as I mentioned, this is far from being trivial, as there exist examples of quantum non-local distributions in this triangle network without inputs. So here is the first example discovered by Fritz in 2012. It's a beautiful idea, I think. I would view the idea as embedding a standard Bell test, CHSH Bell test here in the triangle network, but okay, there might be other ways to think about this example of Fritz, but I think this one is nice and clean to see how it works. So here is the idea. So we are going to imagine now that Alice and Bob want to perform a Bell test, for instance, testing the CHSH inequality. And so they share here some Bell state, right? Now, what do Alice and Bob need to make a CHSH Bell test? Well, they need inputs, right? They need to choice of setting. But here there are no explicit inputs, right? So how we are going to do this? Well, we are going to use these extra sources here in order to provide these inputs. Okay, so these sources are going to distribute classical bit, which represent, which are sort of hidden measurement inputs. And now, so these things, you see, these are given by these sources, but these are local variables that are not shown in the distribution, right? In principle, usually we average over these variables. So here what Alice and Bob must do is that they must reveal these inputs, right? So part of their outputs is going to be the input. And here we have this third party, Charlie, who acts as a sort of referee, if you want. And Charlie is the party broadcasting the inputs, X and Y. And now, so Alice and Bob must produce outputs. Well, because given the inputs, they make the relevant Pauli measurements on their particles. And so these outputs I label here alpha and beta. And of course, Alice and Bob must also provide these outputs. And so here we are basically because we can observe the following thing now. So if the conditional distribution of these outputs alpha beta condition on these effective inputs x and y, if this violates the CHSH inequality, then it must be that the full distribution PABC is not non-local, right? Because otherwise that thing would give you a model for CHSH violation, which of course is not possible. Okay, so this is the example of Fritz. Much later, in fact, only 2 years ago, came another example of quantum non-locality in the triangle network. But this example is intuitively very different from that of Fritz. In particular, the intuition is that it has not much to do with standard Bell non-locality. Okay, so how does this example work? Well, now every party here, every source distributes a Bell state, right? So you see it's already much more symmetrical than before, right? And moreover, each party here performs the same measurement. And this measurement is given here, right? So this is a 2-qubit measurement that has 4 eigenstates that are given here. And you can see 2 of these eigenstates are product, right? But the other 2, they correspond to some entangled state, right? Depending on the value of these parameters U and V. Okay, and so what we could show in this paper is that the resulting distribution, PABC, is non-local whenever this U parameter is in this range, right? So U has to be strictly smaller than 1, of course, otherwise the state would be product here. But okay, so in this range, you can actually prove that the distribution is non-local. The proof is a bit involved, but okay, you can work it through. And you see what is astonishing here, in a sense, is that this is a statement we can make about the ideal quantum distribution, so with pure states and projective measurements. But suppose we would now ask, okay, what happens if we make these states noisy here, if we make them Werner states, for instance, then we have no clue. Okay, this because you see we don't have a proper inequality, such like the CHSH inequality in order to witness the non-locality of this distribution, right? It's something we can only say now for the ideal point. Okay, so now let me go back to something I mentioned before, namely the fact that this new distribution, this new example from 2019 is intuitively quite different from that of Fritz, right? And in fact, when we wrote that paper, we hinted at the fact that this could be a sort of new form of quantum correlations in the triangle that is sort of genuine to the network configuration. But we could only argue, via some arguments, and these arguments are quite simple. So first of all, you see here in this distribution here, we have a high level of symmetry, right? All sources and all parties perform the same measurement. This is, of course, not the case here. There is this asymmetric role with this entangled state on top and these hidden inputs, right? Of course, this means that here we need 3 quantum sources, or let's say we have 3 quantum sources, while here only 1 quantum source is enough. And also the measurements are very different, right? In the Fritz example, the measurements are separable, while in this new example here, the measurements are entangled. Okay, so this is a clear hint, I think, that there is something interesting going on, but then how to actually formalize this. So this is the next topic I'd like to discuss and present you our approach on this question. Okay, so we wanted to formalize a notion of quantum non-locality that is proper to networks, okay? One that cannot be traced back to standard Bell test. So our idea is that we want to view standard quantum non-locality as a resource, right? And so in standard quantum non-locality, what you have? Well, you have some ingredients, which are entangled states and incompatible measurements. And these you put together in order to obtain what I would refer to here as a quantum box. Okay, and let me depict it like this, right? So you see the blue things are the quantum resources, And so this object now is a box. It takes inputs and gives outputs, right? Each party has a terminal with an input and an output. And this box is described again by, quantum decomposition. So any object of this form, I call a quantum box, right? So this is, the standard resource used for Bell test, for standard Bell test. And now what can I do with this resource in the context of a network? So let me imagine this network. Now I can put these boxes in this network. Okay, so each source can now distribute these quantum boxes to the different parties. And now, of course, the question is how do the parties combine these boxes, right? In particular, you see this party here has two terminals. So what can they do with it? Again, it's quite intuitive. They can wire these terminals. So here I have a sketch for this bilocality network with three observers that share quantum boxes. So if I look here at Alice, right, you see it's quite simple. Alice really receives some setting X, inputs X in the first terminal, gets some output, which she may use as an input for the next terminal, and then compute an output. But more generally, wirings can have a very complex structure. For instance, the order in which the terminals are used may differ from one party to the other. And of course, when I have one party like Bob here who receives terminal from different sources, then there can be a very complex structure of wirings, right? So you can have, for instance, dynamical wirings where the output of one terminal will decide on which terminal to use next. Okay, so you can imagine pretty complicated things. So this is all we need to define our notion of genuine network quantum non-locality. We do so, of course, by defining the reverse, right? So we define quantum wireable correlations, which are those that you can obtain in a given network by distributing quantum boxes and wiring them together as you want. Okay, so that's the idea. And so if you can prove that some distribution cannot be realized in this way, right, then we say that it's genuine network non-local. So admittedly, it's pretty difficult to characterize correlations of this form. It's even actually tough to write their form in general. Yet we can find clear examples of genuine network non-locality. But maybe before that, let me give you another perspective on this definition. So you can also think of wirings as classical measurements. And in fact, these are classical measurements in the case where you have several subsystems that need to be combined, right? So their wirings are the classical joint measurements. And so if you have a distribution which you can prove genuine network non-local, you also show that your distribution requires the use of non-classical measurements. So it's another perspective on this idea. So what are non-classical measurements in quantum theory? Well, the first example is clear. You can think of entangled measurements, Bell state measurement, for instance. But it's interesting to note that this is not all there is, right? So you can also have measurements that are separable, yet are non-classical. And so an interesting example is due to Bennett et al., a long ago paper in 1998, where the authors demonstrated an effect now known as non-locality without entanglement. Right? So these are measurements that are composite measurements that you cannot do by LOCC, and therefore you cannot do by wirings. All right, so let me now move to examples of this genuine network non-locality. So the first example is sort of quite disappointingly simple, I would say. This is what is known as event-ready non-locality, which was already there at the very start of entanglement swapping in the first paper of Marek, Zukowski, and others. And so the idea is that via entanglement swapping, right, by having Bob perform a Bell state measurement, one can herald the preparation of an entangled state between Alice and Charlie, right? And this is a setup that was also used in some of the first loophole-free experiments. So it's something very relevant. Now, why is this genuine network non-local? Well, it's the fact that the conditional statistics of Alice and Charlie can violate a Bell inequality, right? And so the intuition is that if Bob would instead apply a wiring here, right? A wiring can only ever create separable states between Alice and Charlie. And so therefore, if Alice and Charlie violate a Bell inequality, they must have entanglement, and therefore it's genuine network non-local. Okay, well, that's a bit trivial, but okay, still an example. But it motivated us to find a much more interesting example, because in principle, the presence of non-locality or Bell inequality violation is not necessary for having genuine network non-locality. And this is exactly what we came up with. So it's an example based on self-testing. So we look again here at this bilocal network. We have again Bell states. Bob makes a Bell state measurement, but now you see the measurements of Alice and Charlie are chosen in a way such that they are local, actually, right? So if you know CHSH very well, you may recognize that whenever Alice and Charlie make aligned measurements, their statistics is local, right? And so this is exactly what happens here, right? So if you take the distribution that corresponds to this experiment, this distribution is local in the usual Bell sense, right? So this means that there is no hope to have event-ready non-locality here. This is not possible. But still, we show that whenever you enforce the network structure, so whenever you assume the independence of these two sources, this experiment here becomes a self-test. So what does it mean? It means that if you want, that this is a sort of black box tomography. When you observe this distribution, well, the only possibility in quantum mechanics that is compatible with what you see is that you have exactly these states here, a Bell state measurement, and these local measurements, right? So this is a self-test. And of course, because it's a self-test, it means in quantum theory, I can only reproduce this distribution via an entangled measurement here, and therefore it cannot be quantum wireable, right? So it must be genuine network non-locality. Well, I think it's a nice idea because you see, again, that enforcing the network structure really allows you to reveal new non-local aspects of your quantum distributions. And in particular here also this sort of strongest notion of non-locality that is self-testing, it can also be enforced by with the network structure. All right, so I see that I have still a bit of time, so I will tell you. Okay, no, maybe let me before moving to the next idea, let me just come back to my initial question, because indeed all this was motivated by comparing the Fritz and the Renou et al. Distribution. So what can I say here? Well, I can say, so if I look at the Fritz, obviously it's quantum wireable, right? Because remember in Fritz, the idea is you make this Bell test between Alice and Bob, and these extra particles here, they only serve as classical inputs, right? So sorry, I did the diagram here in the wrong direction, but you see the idea that there is a clear wiring that can explain the Fritz distribution. Now, for the Renou et al. Case, it's much less clear. In fact, we don't know. We tried hard, but we could not prove that it's genuine network non-local, but we conjecture it highly, I would say. So any progress in this direction would be fantastic. All right, so in the last minutes, let me quickly discuss another idea which connects to no signaling. So as I mentioned in my quick recap at the beginning, the concept of no signaling played a very important role in our understanding of standard non-locality, right? And so, of course, it's legitimate to ask what it tells us here for networks. So the first thing to observe is that networks, right? So there should also be correlations somehow that are impossible in a network in whatever physical theories. Okay, and so one clear example of this is, imagine again this triangle network with outputs that are binary now, and suppose that I see only the case that all outputs take the value 0 with probability half, or all outputs take the value 1. Right? So this would mean that you see ABC have a shared coin somehow, right? But obviously in this triangle network, this cannot be the case, right? Because there is no common tripartite information between the parties. Okay, so intuitively, this distribution, well, we can prove it's impossible classically, quantum mechanically, but in fact, for any generalized theory, this should be impossible, right? And if you find it to be possible in this network, it's because there is a way to signal from one party to the other, right? So no signaling, and the topology of the network should impose constraints on correlations. Indeed, okay, I could have also started this way, actually. So if you think about it, right, how is no signaling usually taken into account in these Bell experiments is because you have inputs, right? So you say one input, the input of Alice cannot affect the statistics of Bob. So usually no signaling is really connected to inputs, but here we have no inputs, right? So how could it be that one party signals to other without having an input? But it's possible. And so here is the mechanism. So let me think now that Alice here would like to try to communicate to Bob and Charlie, right? Instantaneously, to signal to Bob and Charlie. So here is potentially one way she could do it, right? So what she could do is, instead of taking the two particles here and there that she receives from these sources, right? But instead of combining them into a single measurement, she could decide to open the loop, as I showed here, right? And to insert all these extra systems here in her laboratory, right? So now you have to imagine that Alice chooses between this and this whole setup here, right? Now, obviously, from the point of view of Bob and Charlie, right, this choice of Alice can have no influence, right? Because if it would, then that would be signaling, okay? And so, therefore, it's very important, right, that the statistics I see here in this triangle, right, which then also represent marginals of this distribution of this big network here, which is a hexagon, right? So that all this is consistent, right? So I should be able to consistently define the distribution over this more complex network, such that its marginals are compatible with the initial triangle network. And so that is an idea that is known as inflation, that was initially proposed in this paper by Ellie Wolf and colleagues long time ago. Well, in that paper, the scope was more on classical correlation, but can also be applied here in the no signaling case. And so the idea is that when you do all that carefully, well, you can actually work out no signaling constraints in a network that are very strong, and we can even get tight constraints out of it. Okay, so maybe in the interest of time, I will skip my example here, and I will just go directly to the summary and outlook. So I hope I could convince you that the study of non-locality in networks is really a new and interesting area. So I started by discussing classical correlations with the definition of n-locality. And so while here, I would say we still miss really efficient methods for characterizing it. There is the inflation method that I just mentioned, but this is typically cumbersome and not so efficient in practice, gives only weak bounds. And of course, what would be great is to understand how to get strong nonlinear Bell inequalities. Then one could also start thinking about experiments and so on. That would be great. Then I also discussed quantum non-locality, and I hope I could convince you that there is really new phenomena here that occur, right? So first, there is this idea that you can get quantum non-locality without inputs, which is very different from the standard Bell test, and that there exist, in fact, things that are even stronger. So there is this notion of genuine network non-locality that we put forward. So here would be very interesting to have more examples and also further characterization of these sets. Let me mention that there was recently another proposal for capturing correlations in network, that is full network non-locality, by Armin Tavakoli and colleagues. And that has the focus there is more on the sources, right? So remember, in our approach here of genuine network non-locality, we were interested more in the non-classical properties of the measurements, while in full network non-locality, you ask about demonstrating the quantum property of all the sources in the network. And of course, there might be many other interesting effects yet to be discovered. And so finally, I said just a few words about no signaling, right? So how you can actually get no signaling constraints in a network, and this is via this idea of inflation. So by locally changing the topology of the network, you should not be able to signal. But of course, there might be other types of constraints, right? This we don't know. That is still an open question at the moment. Right, so overall, my message is that this is a very interesting but tough problem, and of course it also opens many opportunities. So if you have nice ideas, if you know about strong mathematical methods for handling non-convex problems, well, here you may have something very interesting to say. Okay, and with this, let me conclude, and thank you for your attention.
Thank you, Nicolas. There's a question by Reinhard Werner there.
So I've been working more with the convex side. So the natural question here, the natural question here is how does this all change with shared randomness? I mean, that you could incorporate, clearly this all zero, all one example could easily be done with shared randomness. And that would bring you back into a convex setting.
Yes.
Now, that could also be simulated by an additional node that distributes this classical information, for example. But does the problem, as you stated, trivialize when you allow shared randomness?
Yes, that's true. At
okay,
least
that's what I suspected. Yeah. Okay.
At least in the case where you have no inputs, right? And if the shared randomness it can be perfectly distributed, right, to all sources. So if there can be maximal influence, if you want, then it becomes trivial. However, perhaps one scenario that goes in the direction you suggest, but that is sort of intermediate, is if you would imagine adding a central source, right, in the triangle network. And so this source could, influence the other sources and the parties, but only in a limited way, right? So if you assume partial correlations between the sources. And in fact, in that case, we could actually show that even if you have an arbitrary level of independence between these sources, right? So the central source can, correlate perfectly, correlate almost perfectly to all the sources, yet you can still demonstrate quantum non-locality.
There is an online question, so we can move to it.
Should I do something, Valerio? Sorry,
No, you should not do anything. There's a person online who should ask a question.
Hi, can you hear me?
Yes.
Yes, I would like to make a comment more than a question because I do not know how familiar you are with the idea of retrocausality. So the types of systems you consider as sources are either quantum or classical. And I think it would be very interesting to generalize and to consider also the types of toy models we have discussed for Bell non-locality. So there is one toy model, which is the Schulman model. I can give you references and so on. And it describes the behavior of the polarization of a photon, of a pair of photons, Bell correlated, and in a way that depends on the settings which are in the future. So it's the ontic variables depend on future inputs. Mm-hmm. And that opens, of course, endless possibilities. You can, of course, explain everything that way. But if you stick to just this specific model, you may discover interesting correlations which are possible or not possible. And it would, of course, be very interesting to see what quantum correlations can be described by this model and what could not.
Mm-hmm, mm-hmm, mm-hmm. Yeah, so if you could send me the reference, that would be great.
Yeah, sure.
But perhaps one thing I can comment on that is that in the very last part of the talk, I went beyond just classical or quantum sources, right? The part about non-signaling, there we can derive bounds that would hold in any of these, well, I don't know if you're familiar with them, but so-called generalized probabilistic theories. So theories that satisfy the no signaling principle, right? But that can have a structure that is different from quantum mechanics. So essentially, all these theories, they have to satisfy quite strong bounds on their correlations in networks.
Yes, of course, but they also realize possibilities which are not allowed by quantum mechanics. So they're not physical, right? And the idea here is maybe to build a reformulation of quantum mechanics in terms of some ontic variables which do depend on future inputs. So it's not the standard ontic variable picture. And it's not known yet if this is possible or not. So it would be very interesting.
Mm-hmm.
Thank you.
Okay, do we have another question online or offline? So, meaning live. Reinhard has another one.
I'd just like to know whether you have a connection to what's called algebraic statistics. So there is a book on that by Bernd Sturmfeld, and they seem to have similar problems. So I'm just curious whether you have made that connection at some point.
No, not at all, but thanks for mentioning it.
Okay.
Algebraic statistics?
Algebraic statistics. Funny title, but they do have independence constraints, and there will be some relation, I'm pretty sure.
Cool. Okay, I'll check it out. Thanks.
We have another question online. The person can probably already ask it.
Yeah, can you hear me?
Yes. Salut, Cyril.
This is Cyril Banciard from Grenoble. Thanks for the talk, Nicolas. I'm still pretty confused by your definition of classical measurements via wirings. So I was wondering if you could clarify how this compares to LOCC measurements between the different systems that you receive from the sources.
Mm-hmm. So in general, LOCC measurements are going to be LOCC measurements are going to be stronger than wirings. The reason I refer to wirings as classical measurements is that wirings are joint measurements that you can do for any theory, right? So LOCC already refers to quantum, but wirings you could apply to whatever, right? So I think in that sense, they are the minimal sets of measurements that you would have in any theory.
Could you say it's the natural generalization to any theory of LOCC?
I'm not sure if it's a generalization of LOCC because I think it's weaker, right? So I think in quantum mechanics, there would be measurements that you cannot do with wirings, but that you can do with LOCC. Because you see, in LOCC, wirings is just about terminals, right? While LOCC, you can go inside the boxes and do some some quantum operation and then connect to the other one.
Okay, so then there is stuff that you can do with LOCC that you wouldn't call classical. Is that?
Yes, I think so.
Okay.
There is a very nice paper by Miguel Navasquez and Tamás Vertési that discusses these different types of measurements. And okay, I think it's worth going to check there because they thought about this problem. And I remember there were some interesting examples showing the differences.
Okay, thanks for the clarification.
Okay, we are perfectly on time, so we can thank Nicolas again.
Thank you.